Pencast 7. This is 7.22 from the book. We have a two discs, one smaller one of radius A, and then a bigger one of radius B, separated by distance Z, little b, little a. Okay, so in part A, we're said suppose there's a current I going around this bottom loop, and we want to find the current through the little loop, and we're told it's so small that we can consider the field of the big loop to be essentially constant. So we're going to do that. So we need to find the flux through A. So since we are moving around this way using right hand rule, we have a B going through like that, and also the dA component as well. And then this magnetic field's one we've solved before and solved in example 5.6 in Griffiths as mu naught I over 2 b squared over b squared plus z squared to the 3/2 in the z hat direction. Then the magnetic flux is the integral of b dotted with dA. These two are parallel with each other, and we were allowed to assume that b is approximately constant. So we have b times the integral of dA, or BA, which is pi a squared b, or mu naught I pi a squared b squared over 2 b squared plus z squared to the 3/2. That's for part A. Part B. Now we are told we to now assume that the current is in the little loop. And we're allowed to assume that it's so small that this is a magnetic dipole. So since we can assume that, we have mu naught over 4 pi r squared, r cubed, 3m dotted with r hat in the r hat direction minus magnetic dipole. So real quick, right here, we have our z hat direction and our r hat direction at an angle theta. That's in both the spots. And then we are looking not to B, but to any arbitrary point along any arbitrary dA on here. So with that set up, we have r is equal to the square root of s squared plus z squared, the magnetic dipole, which equals the area times the current. The area in this case we have pi a squared, and that is in the z hat direction, once again from the right hand rule, times I. Thus, m dotted with r hat, we get pi a squared I for the magnitude of m. Magnitude of r is 1, and the angle between these two is cosine theta. And from here, cosine theta is just adjacent over hypotenuse, or z over r. So then b equals mu naught over 4 pi r cubed, or z squared plus s squared to the 3/2. We have our 3, then our m dotted with r hat, pi a squared I z over the square root of s squared plus z squared in the r hat direction, minus m, which is the pi a squared I in the z hat. And one last step, You can pull the pi a squared I out. Okay, so that's the magnetic field. I wish I could say we were done, but no, the magnetic flux now. Once again, we have the integral of b dot dA, which I'm going to write as the integral of the arc component dotted with dA plus the z component dotted with dA. The r hat component, the dA is once again in the z hat component, and the r part's in the r hat component. So we're going to get we're going to get integral of br dA, and then another cosine of theta, or z over r. The z component and dA are in the same direction, so we're just going to get the integral of bz dA. So when writing these out and doing some simplification, actually first I'm going to write out, doing some simplification and noting that dA is s ds d theta, and we have no d theta else here, so the integral of d theta is 2 pi, so I'll pull that out also. Then the integral from of 0 to b, 3z squared s ds over s squared plus z squared to the 5 halves minus the integral from 0 to b, s ds over s squared plus z squared to the 3 halves, after putting in for the z over r and doing some simplification. So now u equals s squared plus z squared, du equals 2s ds, or 1/2 du equals s ds. We can now write this then, give u naught a squared, I 2 pi over 4, integral from, I'm going to pull the 1/2 from the du. So 3 halves z squared, integral from b squared to z squared plus b squared after redefining our limits. And then we have u to the negative 5 halves du minus 1/2 z squared to z squared plus b squared, u to the negative 3 halves du and from here it's just going to be a whole bunch of integration, and for the sake of the person holding the camera right now, I'm not going to go through and do all that integration. But it's simple from there on out, and then it's algebra. So we're going to end up after all this with mu naught pi squared a squared b squared I over 2 b squared plus z squared to the 3 halves, which equals the magnetic flux. And that's the answer for part B. And if we notice, the answers to part A and B were the exact same, which is important to the next part. With mutual inductance, we're now wanting to find the mutual inductance for both of these and show that they're equal. So that is defined as the flux divided by I. So we're just dividing I out of both of these fluxes. Since they're the fluxes are the exact same thing, and we never changed I. For the first one, we get this, the term for magnetic flux just without the I term. And for the second one, since it's the same thing, and we're dividing out the same thing, you can get the exact same answer, which just shows that M12 equals M21, like we wanted to show. Done.